Okay, let's take a look at an example, a step response of an RC circuit with just a little more complexity to it. We're going to have, or start out here with a 24-volt source and a switch that at t equals 0 closes. And this time, instead of having just a simple resistor that the capacitor is charging through, we're going to have a little bit more of a resistive network. Let's say that this is a 5 kilo ohm resistor and this is a 15 kilo ohm resistor, and this capacitor is 1 microfarad. Alrighty, for t less than 0, there's no charge on the capacitor. Had there been charge on the capacitor in this case, it would have drained through the 15 kilo ohm resistor. So we assume that it's been in this position for a long time, such that V sub C, let's define the reference directions. We've got plus to minus V sub C, and again we're going to define the current in the passive reference going from the positive to negative voltage. So V sub C at 0 minus equals 0. So V sub C at 0 plus also equals 0 because it won't change instantaneously. Now, V final, a little more complexity here on this. What will this capacitor charge up to? Well, it's going to charge until there's no more current flowing through this capacitor. It's going to charge until this capacitor is effectively an open circuit. An open circuit meaning that it's open, there's no current flowing through it. At that point, if there's no current going this way, all the current through the 5K resistor will also be going through the 15 kilo ohm resistor. In other words, with this fully charged, we've got a voltage divider situation. And the voltage across the capacitor, as t approaches infinity, the final voltage is going to be 24 times 15 over 5 plus 15. It's just going to be the voltage across that 15 kilo ohm resistor as t approaches infinity. And this then turns out to be 18 volts. Let's just look at this a little bit more closely. Right when it switches, and there's no voltage across this capacitor, just for an instant, this is effectively a short circuit, and the current will go directly to the capacitor, this resistor, only for the instant that there's no voltage on here. This 15 kilo ohm resistor is shorted out by the capacitor. And so that initial current is going to be the 24 volts divided by the 5 kilo ohms. We'll get to that in a minute, a little bit later. But as soon as we start getting voltage on this capacitor, we then have voltage across the resistor, and we have current coming here and here. And then ultimately, as we've already pointed out, when the capacitor is charged up to its final value, there will be no current going here, and all of the current will continue through the 15 kilo ohm resistor. So our final voltage then is going to be 18 volts. It's just the voltage across that we calculated from the voltage divider. Tau for this circuit is going to be R times C, which is equal to R. Which R do we use? We use the effective resistance that this capacitor is exposed to. The equivalent resistance seen looking back into that circuit. Now don't let this blow your mind, but that's the Thevenin resistance. The Thevenin resistance, we'll call it Req, can be found by deactivating this voltage source, i.e. turning it to 0, which brings the 5K and the 15K into parallel with each other. So Req is equal to R Thevenin, which we can get from method 2, deactivating the source and looking at the resistance that results, which is the parallel resistance of the 5 and the 15. And that resistance is equal to 3.75 kiloohms. Write it down here, 3.75 kiloohms. So tau then is going to be 3.75 times 10 to the third, that's the value of R, times C, which is 1 times 10 to the minus sixth. Our tau then is 3.75 times 10 to the minus third, or 3.75 milliseconds. Okay, and we know that the voltage across the capacitor as a function of time is equal to V final plus V initial minus V final, e to the minus t over tau. We simply plug in the value. V final is 18 volts plus the initial voltage of 0 minus the final voltage of 18, e to the minus t divided by 3.75 times 10 to the minus third seconds, which is equal to 18 minus 18 e to the minus t over 3.75 times 10 to the minus third seconds. Let's graph it. It starts at 0. It's approaching 18 volts asymptotically. And out here at 4 tau, I'm just going to write it as 4 tau, 2 tau, tau, 3 tau. So 4 tau would be 4 times 3.75 milliseconds. What is that? about 14 seconds, something like that. And what is it? Get the calculator out here. 4 times 3.75. 4 times 3.75 is 15. So out here at 15 milliseconds, that capacitor will be at its within 1% or so of its final value.